All right. So yeah, your exam 3, you guys still did very well overall. It's 82, I think 82.1% overall. Okay, so that's pretty good still. Okay, so keep it up. Um yeah, and then this exam, I think it's a little bit more difficult than the previous two. Okay, and then the last week exam should be a little bit easier than this one. So you expect the final to be a little bit easier. Okay, so you guys are still on good track. All right. um. So for the lecture part, we will start chapter 14 on fluid mechanics. So before that, I just want to remind you guys, homework 10 is due on Wednesday, okay? Um, and then for today's classroom disinfection, Isaiah and Joshua, okay? All right. So, um, so we kind of switch topic a little bit here from today on. So we'll be talking about fluids, density, and pressure, okay? So fluid um, includes both liquid and gases. Okay, so basically, if the material is not having defined shape, that means if you have a container, the material will fit into the container with the shape. Okay, so then it's considered to be fluid. So basically, any liquid, any gases are considered fluid. Okay. Um, so basically, if you have solid, then pretty much the atoms inside the solid, they are fixed at locations. That means the variation, change in locations are very small. Okay. Uh, on the other hand, for fluid, then the molecules or atoms can be moving actually quite freely throughout the body. Okay. So that's the difference between fluid and solid. All right. So the first thing here in this chapter talks about density. I think you guys know how to calculate density. So basically, mass divided by volume, that will give you density. And then I believe you guys had a lab on this one, how different materials and different shapes. Okay, so M divided by V. Density, you use rho as the letter, the symbol for it. Okay, looks like a P, but it's rho, called rho. M is mass, and then V is for volume. Okay, so for the SI unit for density, it's going to be kilogram per meters cube because mass should be in kilogram and volume, the dimension should be in meters cube. Okay, now there's another unit you guys may encounter often. It's called CGS units. That means centimeter grams second unit. Okay, instead of SI unit. So that's also used often. So I believe in the lab you guys use CGS unit for the density. Okay, so G over centimeter cube. All right. Some densities, some materials, their densities are listed over here. Okay. If you need some of the numbers, you can refer to this table. Okay. Now, most of the materials, the density varies as temperature increases. Okay, or actually, the density decreases as temperature increase because you expect that when temperatures increase, the volume, the dimension will expand, right? But the material, the M stays the same. So you typically expect that when temperature is higher, then density is lower. But for water, it's actually having a very unique region that when the temperature increases from 0 to 4, actually its density also increases. All right. Now, after 4 degrees Celsius, then that's the same in that sense. Okay. The same trend goes that way. Now, we are talking about the same pressure over here. Okay. So that's for the water, okay, and then not having a phase transition, so this is all in liquid form, okay, compared to the steam. That's a different story. So if you look at the density versus temperature curve, then this is what you would expect for water, okay. So from 0 to 4 increases, then decreases. All right. All right, so let's take look at this example. suppose you have a coffee mug with a circular cross section and vertical sides. That means uniform radius. Okay, so what's its inside radius if it holds 375 grams of coffee when filled to a depth of 7.5 centimeter? Use the density of the coffee as 1.00 grams per centimeter cube. Okay, so that's the same as water at 4 degrees Celsius. Okay. I'm sure you guys know for the volume of a cylinder, it's equal to the area times the height. So area, cross-sectional area should be pi r square. Okay, I think you guys know this, but just in case, if you don't remember it right away, okay. All right, so we can take a look here together. So density is equal to mass divided by V. You're looking for R. Okay, so in this case, you want to replace A with this guy, right? So then this is rho equals to M divided by, for the volume, it's going to be pi R squared times H, right? H is the height given. From here, you'll see that then R, you're going to just put R on this side, right? The equation, and then put rho down here. So then R squared equals to M divided by pi times rho times H, right? So then you'll take square root to the both sides of equation to get your radius equals to square root of the mass, okay, which is given as 375 grams. All right. Now, I think in this problem, the units are given as CGS, the centimeter, gram, and second unit. So we can keep the CGS unit, okay? 7.5 centimeter. So then the result will be in centimeter, okay, if you use CGS unit. So I think I got 4.00 centimeters, okay? So many of you guys have pretty much the same, okay? It's 3.99, okay? So that would be this guy, okay? All right. Okay, so let's move on here. Um, Now, most of the time, we can consider that the density of the um, substance or fluid is uniform throughout the body. Okay, but in reality, if the change in depth is very large, then actually it's not necessarily uniform throughout the body. Okay, so you can see here from different locations, you might have different densities. Okay, if the depth change is large enough. Okay, so then variation of density throughout the body, then we can call the any given position, the density at that position to be the local density. Okay, so that's the term local density means the density at some specific location. So it might depends on the location X, Y, and Z if this is three-dimensional. Okay. So in that sense, then density is defined as taking the limit of a small volume approaching zero and then change in mass divided by change in V, okay? Or I can do derivative of M over derivative of V volume, okay? Now, another term you might heard often is called specific gravity. So that's the ratio between the density of a certain material with the density of the water at 4 degrees Celsius. Okay, so at 4 degrees Celsius, water has a density of 1 grams per meters cube or 1,000 kilograms per or 1 grams per centimeter cube. Okay, or 1,000 kilograms per meters cube. So if the problem gives you specific gravity, that means ratio of two densities. So then it will just give you a number without any unit because the unit will cancel out. Okay. So then, for example, specific gravity for aluminum then should be 2.7. So you basically do 2.7 gram per centimeter cube divided by 1 gram per centimeter cube. That gives you 2.7. Okay. All right. So the second quantity here is pressure. So pressure, I think we briefly mentioned this when we are talking about deformation of material. It's defined similar, the same as stress. So pressure is equal to force divided by the area under the impact of the force. Okay, so F divided by A. Now you might imagine that pressure will be having particular direction. Okay, so in reality, that's also true. But if we are talking about fluid, then pressure is in all directions. Like if you are inside fluid, so pressure comes from all directions, right? So in that case, we will say pressure is a scalar quantity. Okay, so we don't have to worry about the direction. So just treat it as a scalar quantity. Okay. Um, the SI unit for pressure is newtons per meter square. So newtons come from force, meter square comes from area. Okay, and it has its own name called Pascal or PA for the symbol PA. All right. Other unit you might you may hear often is like PSI stands for pounds per square inch. Okay. And then ATM is the atmospheric pressure. Okay. And then also in chemistry, you may often hear like millimeter mercury. Okay. So in that sense, there's different units that involve. So I think there's a table in the next slide, but let me just, before going to the next slide, let me just refer to again. So pressure will change at different locations often. So then we should be referring to also the local pressure, okay, defined as dA derivative of F divided by dA, okay. So it's location dependent. So from the definition, you can see F divided by A. So if you have the same force but different areas, then for small area, you will get the larger pressure versus to the for larger area, you'll get small pressure. Okay. Let me see. Looks like I forget. Oh, the units. Yeah, there's quite a few slides away. So yeah, we can you can take a quick look, or we can refer to this later on. So you can see different units here. You would like to know the conversion, okay, between units. Okay, so that's the key there. All right. But let's go back. Okay, let's take a look on the second example here. This one is on pressure. So it says nail tips exert tremendous pressures when they are hit by hammers because they exert a large force over a small area. What force must be exerted on a nail with a circular tip of 1.00 in millimeter diameter to create a pressure of 3.00 times 10 to the 9th newtons per meter square. This high pressure is possibly because the hammer strikes the nail. Striking the nail is brought to rest in such a short distance. Okay. Pay attention to the units there. Okay. So the area in terms of diameter should be 1/4 pi diameter square. Okay, so this one is given your diameters, and it gives you the pressure 3 times 10 to the 9th Pascal or newtons over meter square. So you're looking for force. All right. So let's see here. You're looking for force here. So then from the definition, you can figure that force should be equal to pressure times the area, right? area is that guy, so then it's 3.00 times 10 to the ninth Newton meter square over meter square times the area 1.1/4 times pi now times 1.0 0 times 10 to the minus 3. Okay, you want to square this term over there. Okay, so it's about for many of you got this right, 2.36 times 10 to the third newtons. Okay, roughly. Okay. All right. So as I mentioned, the pressure will vary as location. So pretty much if you look at the say a water here in this container, a cylinder container over here, right? So pretty much, so if we say if this is vacuum over here on the top here, then it's pretty much the weight of the water above it. So let's look at the bottom here. Okay, so to pretty much the weight of the liquid above it divided by the area, right? Because all the weight will be exerted on the area at the bottom over here. So then pressure is equal to mg divided by A. Okay. If you multiply the numerator and then also denominator by h, okay, so both by h, then at the bottom here you will have A times h, which is the height of liquid. Okay, that equals to, so A times h will give you the volume of the liquid. Then mass divided by the volume will give you the density here. Rho is the density of the liquid. Okay, so then rho times gh will be equal to P. So you can see clearly P is proportional to h. Okay, the depth of the liquid. Okay, or the height of the liquid. So rho gh. All right. Now, if this is not vacuum, if this is open to air, then P should be equal to the atmospheric pressure plus the rho gh. Okay, so whatever that pressure is on the top plus this, the pressure that by the weight of the liquid. Okay, that will be giving you that. Okay. All right. So we have the previous formula assuming that the we are in the uniform gravitational field. Okay, so and then for most of cases, you can assume that because um, the gravity doesn't change very much, even over like say kilometers of distance. Okay, because the Earth's radius is like 6,300 something kilometers. So even like in a depth of 1 or 2 kilometers, it doesn't change g very much. Okay. But if you look at the local pressure, okay, so then you can see here the variation of pressure with the height or the vertical position y. So you can take a look on a small slice of the liquid over here. So because this is in static equilibrium, right? The liquid is in static equilibrium right now. So then this piece of liquid, the pressure by the bottom from the bottom here should be equal to the pressure from the top plus the weight of this liquid itself. Okay, so you can do it that way. So for the free body diagram there, so then three forces add up to be 0. Okay, one positive, two negatives. And then for delta M of that slice is equal to the density times the volume. Okay, so density times the volume will be equal to cross-sectional area times the thickness of delta Y. Okay, so or minus rho A delta Y. Okay, so because you take positive to be up in the upward direction, so then this change in the thickness is minus. Okay, so then take that into this equation over here. Delta M is replaced by minus of rho A delta Y. So then you'll arrive at this equation over here. So basically, it's going to give you this guy minus this guy equals to the other side of the equation will be minus rho g. Okay, you put that y there. A will cancel out across. Okay, so then that's equal to that guy. On this one, if you are doing derivative form, then it's dp over dy, and that equals to minus rho times g. Okay, so as the depth increases, then the pressure also will increase if you are going in a negative direction. Okay. All right. So from this one, then you can revisit what we learned a couple of slides back. Okay, you can actually take a integration of this guy from P0 to P, and then from minus 0 to minus H. So you're going from the top here, the surface over here, going down into the liquid, okay, in the y direction. Then you will arrive at the same expression over there as well. Okay, so P at any point, particular point down here is equal to P0 at the top here plus rho GH. Okay, so basically the same equation. All right. Another feature for fluid, the pressure at the same height will be the same. Okay, it doesn't depend on the shape of the container you have. So you can have like this, if you have a device like this, they are all connected at the bottom over here. So then on the top level here, you will have the same height for the surface, because at the bottom here, or here, or here, or here, you will have the same pressure. Okay, so the pressure is only depends on the height. Okay, so it doesn't depend on the shape over there. So then you'll see that will be at the same level on the top surface. Okay. All right. So I think we have checked on liquids specifically, but as we mentioned earlier at the beginning of the chapter, we say air is also a fluid. Okay, so then the similar will apply to the air. So we are at the bottom, at the surface of the Earth here. So then pretty much the pressure, the atmospheric pressure, it's actually the weight of the air molecules above us, okay, and then divide by the area. So if you take, say, whatever, say 1 meters square as the cylinder here above, then the weight of all this air molecule add up, divide by this area, will give the atmospheric pressure, okay, on the surface of the Earth. At the sea level, this pressure is called 1 atmospheric pressure, which is equal to 1.01 times 10 to the 5th Pascal, okay? Or you can call it 1 ATM, all right? And as I mentioned earlier, directions for the pressure inside a fluid. So it's actually going into all directions. Okay, so if you are, say, if you are swimming, actually pressure comes from all directions. Okay, so towards your body. And then over here, if you have a tire over here, then pressure on the inner wall is going into that direction, and the outer wall is going into that direction. Okay. So you can say pressure has no direction because it's going everywhere, or you can say it's in all directions, okay? All right. So next, let's take a look on the device that we often use to measure pressure. So it's called the pressure gauge, okay? So for pressure gauge, it reads the pressure with respect to the atmospheric pressure. Okay, so then the actual absolute value for the pressure. So this is relative pressure. Okay, so the absolute pressure then will be whatever the gauge reads plus the PATM. Okay, so then that's the what you need to add up. Okay, so next semester when you guys I think there's one lab involving, you are going to use a pressure gauge. Okay, then you'll be adding the atmospheric pressure for that. Okay, for the absolute pressure. In chemistry, the pressure is often represented by the height of the mercury. So this is the very early version of the barometer, mercury barometer. Okay, so um, in order to achieve the atomic pressure, so what you do is you fill this tube. So this tube is one end open, and then the other end is sealed. So you actually put it on the seal end to be at the bottom, and then open end upward. Then you'll fill with the mercury to the top. Okay, and you kind of probably put something to seal the open end, and then flip it over, and then dip it into a mercury bath over there. All right. So initially the mercury is up here, then it probably will be dragged down because of weight. So then this is vacuum here created. Okay. So for vacuum, you have zero pressure. So then for the pressure built up over here at the surface over here, okay, so it would be equal to the weight above this point divided by the cross-sectional area, okay? And you can kind of derive that the pressure should be equal to rho GH, okay, just like what we derived a couple of times earlier, because this is liquid, right? So it depends on the height of the liquid above it. So rho GH will be the pressure over here. And then if you have mercury, so then it's about 760 millimeter height, okay, or roughly 30 inches height, okay. So for the mercury, then at this point, the pressure at this point should be the same as the pressure over here, which is the atmospheric pressure, right? Because over here, that's equal to all the airs above it divided by this cross-sectional area, okay? So then here and here, you should have the same pressure, okay? Because that's the same height, all right? So in that sense, pressure is sometimes referred to the height of mercury, okay? All right, and then here comes the unit conversion here, okay? So if you are working between two different units, you know how to convert them, okay? You can look up this over here, okay? So 1 ATM is not exactly 10 to the fifth, but 1.013, okay, times 10 to the fifth, okay? But 10 to the fifth Pascal is called 1 bar, all right? So there's a lot of different units over here. And then 1 torr is 1 millimeter mercury. Okay, that's 122 roughly in Pascal. Okay. All right. So next section here is called Pascal's principle and hydraulics. So we know by now that the pressure inside liquid acts in all directions, right? So then you can see it actually is also uniform, all right? So if the height variation is not very big, then it's uniform. So for most of the cases, we can assume in that way, unless otherwise stated, okay? So you can see pressure over here is the same as pressure over there, and pressure here, and then pressure on the wall, okay? So this is called Pascal's principle. It says all change in the pressure of an enclosed fluid at rest is transmitted uniformly to all points in the fluid. So for example, if you add 50 kilogram of weight on top of that, so then the pressure inside this here enclosed fluid will change, right? Now, once this is changed, then this is changed as well accordingly. So it's if you say if this is increase of say 500 Pascal, then pressure on this wall will be increased by 500, and then at the bottom here should be also changed by 500. Okay, so any change on any direction of the pressure, then it will affect the other directions as well. Okay, so that's the Pascal's principle. And then due to of that, actually you can design a hydraulic device or system like this, right? So on this end, you can have a small cross-sectional area. So as your input, okay? if you apply a small force here, divide by this small area, so the result may be change in significant in pressure on this side. And you can have all this connected to the other side where you have a larger cross-sectional area. So you can apply small force here. The result here is having a relative larger output force, okay? And then that's the hydraulic device we use. For example, in a garage, the mechanics garage there. So typically there's another part that's not showing in the figure, but it's a small area where you can apply small force, then you can lift up a relatively high, heavy object like that, okay? But basically, the principle over here is F1 over A is equal to F2 over A, okay? Because pressure on this side should be the same as the pressure on the other side, okay? All right, so we will take a look on this one here. This one says hydraulic brakes use Pascal's principle. The driver exerts a force of 100 newtons on the brake pedal. This force is increased by the simple lever and again by the hydraulic system. Each of the identical slave cylinders receive the same pressure and therefore creates the same force, output F2. The circular cross-sectional area of the master and the slave cylinders are represented by A1, A2, respectively. Given the numbers in the figure, you can calculate what's F2, okay? So there's a simple machine over here, and then there's this hydraulic system over here. So from here, connect to the brakes to the tires, okay? So these are all filled with the fluid, okay? So that's A1 here with a diameter of 0.5. Another cross-sectional area here is having diameter of 2.5, okay? So if you apply 100 force here, newtons of force here, what's the resultant of F2 on each of the brakes here? Okay, you guys can give it a try. We can take a look at the solution later. So let's take a look here. So there's a lever here. If you apply 100 Newton force here, okay, so let's say, so this is not exactly horizontal, but let's take an approximation that this is horizontal applied over here. So if it's 100 over here, lever arm is 0.2, so then you'll be doing 100 newtons, right, times the lever arm of 0.2 meters equals to this, the first output force, okay, that's applied over here, F1 times 0.040 meters, right? Then you can solve for what would be this force, okay, F1. Okay, so basically 100 times 0.2 divided by 0.04. All right, so that would be 500 newtons. All right, so the 500 newtons then is applied to this part over here where this is liquid inside here. So this is the master cylinder over here with a piston on top. So then F1 over A1 is going to be equal to, because they are all connected with the liquid, so then it will be equal to this F2 divided by A2. Okay, so then the next will be F1 over A1 equals to F2 over A2. Okay. So in that case, now area should be equal to, it gives you the, again, diameter, so pi over 4 times d squared, right? So then this would be F1 over pi over 4 times d1 squared equals to F2 over pi over 4 here, d2 squared. And you can realize that actually pi over 4 will cancel out, right? So then you don't have to plug in the pi over 2 into your calculator twice. So then F1 over D1 squared is equal to F2 over D2 squared. Now you're looking for F2. So F2 should be equal to F1 over D1 squared times D2 squared. Okay. F1 is the 500 newtons divided by D1. Let me see the number. D1 would be 0.5 centimeter square, okay? Times D2 would be 2.5 centimeter square. You can also check on the problem to see the numbers. You don't have necessarily have to convert the centimeters, right? Because they will cancel out, okay? So you don't have to convert those, right? So then 5 over 2.5 over 0.5 will give you 5. 5 squared will be 25. So it'll be 25 multiplied by 500. That's going to be giving you 12,500 newtons. Okay, so that's the output force as a result. Okay, all right. Let me know if you have questions on this one here. So if not, then I think we are going to just stop here for today, okay? And then come back for lecture online tomorrow, okay?